Hello guys, welcome back to MJ School of Mining and Geology. In today's lesson, we are dealing with mass-independent fractionation and mass-dependent fractionation. We are basically looking at Cap 33 ratio, all right, looking specifically at the case of the Bushveld Complex, where in this the Cap 33 sulfur isotope ratios, okay, which are we call them mass independent or non-zero isotopic signatures. They are usually used as the contaminant tracer. Okay, so please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. Stay tuned. So basically, sulfur, it has atomic number 16, and it has got isotopes 32, 33, 34, 36, which are stable. And we've got the radioactive one, which is the sulfur 35, all right? And then sulfur 32 and sulfur 34, they are most abundant. If you can check here, they are the most abundant ones. So usually they are used for the ratio sulfur 34, okay? So they're used for this ratio. So yes, so this ratio, it's wherein you're taking sulfur 34, okay, sulfur 32. Okay, so this is because these are abundant. But today we are not looking at the sulfur 34. And then also, we also have the one for 33, wherein the ratio for 33, wherein we are taking sulfur 33, okay, divide that against sulfur 32, all right? So now, if we are taking this, okay, if we are taking this one, we can say we determine what you call cap 33, wherein this was from, okay, minus, and then 34 divided by 2. This will always approximate, or the assumption was it's going to be approximate to 0. That is cap 33. So today we're going to be looking at this, the importance of this one as the important tracer. Okay, or it's like a human fingerprint. All right, you know the human fingerprint. If you commit a crime here, and let's say you run somewhere far, they still gonna, if they use your fingerprint, they will know exactly who did that. Okay, so that is the sulfur isotopes. All right. So these sulfur isotopes, they are very important in specifically magmatic systems. So today we're gonna also be looking at what you call the magmatic systems. But first, we have to understand the major event which happened approximately between 2.45 and 2.32 billion years ago. This it's what you call the Great Oxidation Event is basically a rise in oxygen levels, which was due to the presence of the photosynthetic life forms like cyanobacteria, all right, like cyanobacteria, all right, these life forms, cyanobacteria that were living in the sea. Okay, so this rise in sea level due to these photosynthetic life forms like cyanobacteria, it gave rise to an oxygen, all right, which led to a major shift in the Earth environment. All right, so these cyanobacteria were giving out the oxygen as their byproduct. It means they were not using the oxygen, and then this a rise in oxygen level, it's referred to what we call the great oxidation event, which is highlighted here. Okay, so this is very important event because it changes, or it changes the environment. Okay, there's a major shift which happened here. So it divides the reducing environment from the reducing environment from oxic environment. But I'm gonna explain to you now why this Great Oxidation Event was very important. Okay, so what happened was in the early Earth. Here we have what you call it the Archean. Okay, what we see the mass-independent fractionation, but in this mass-independent fractionation, they happened before the Great Oxidation Event. They happened before this major event, okay, which caused a major shift in the Earth environment. So the mass-independent fractionation, they happened before the Great Oxidation Event, but mass-dependent fractionation, they happened right after the Great Oxidation Event. So if we can check, all right, first we have to understand basically what do we mean when we say something is mass independent. It means the fractionation or the separation, it happens independent of their masses. Okay, but if the fractionation happens due to the mass difference, we call it mass-dependent fractionation. Okay. So if I were to, give you example in terms of the mass dependent, all right? This is the fractionation which is predictable and it follows the normal rules. Okay, so it follows the normal rules because we know that the Cap33 sulfur isotope ratio, it must equal to 0. So it must always be on the line, on this line, on the 0 line. So if you can check all these points, they fall on the 0 line. It means they obey mass-dependent fractionation. Okay, so this fractionation is predictable. All right, this fractionation is predictable and it follows the normal rules. All right, so in sulfur isotopes, if we to give you example, looking at specifically sulfur isotopes, right? The mass-dependent fractionation, it affects isotopes like sulfur 34 and sulfur 36. But now the relationship between isotopic ratios remains consistent and they are predictable. The most important part is these are consistent and they are predictable because they they fall on the 0 line. All right. So these are the this Cap33 ratio is always equal to 0. All right. So which is why they are consistent and they are predictable. Okay. So can you now see that if this mass-dependent fractionation, they are common in this environment, in this recent Earth, wherein we are in what we call an oxic environment. We're in what you call the oxic environment or environment with oxygen. Remember, in the during Great Oxidation Event, that's where we had what you call the rise in oxygen level due to that presence of cyanobacteria. So now it gives us the upper atmosphere to have what we call the oxygen or the high level of oxygen. So now so because now the modern Earth, it has got oxygen in it. Now, this presence of oxygen, it was very crucial in sense that if we had what you call the UV light, we have what you call UV light. So the UV light, it was, this associating the sulfur compound, like sulfur dioxide. So when these UV light, they were hitting this sulfur dioxide, the sulfur dioxide dissociated into a sulfur and something like that. All right. So what happened was, now after this dissociation, we had what we call a recombination and the reaction. So after this, we had the reaction that was happening. We had the reaction that was happening, and we also had what we call the recombination. Okay, so now after this reaction and recombination, due to the presence of what? Of oxygen, due to the presence of oxygen, because we had the oxygen. So it means now these sulfur products, all right, were now, reoxidized now the reaction during this reaction, and then they recombined. Now making sure now that the MIF isotopic signatures these signatures were not preserved in the rock record, which is why the rocks after a great oxidation event, they are not supposed to be containing the MIF values. Okay, but now the mass-independent fractionation, these are what you call the non-zero. They do not follow the normal rules where the isotope fractionation is proportional to the mass difference. No. Now they do not follow that relationship or that rule. All right. The fractionation happens independent of their masses. So we call these things non-zero isotopic signatures. They are non-zero isotopic signatures because they are not on the line. So they can either be negative or they can either be positive. So we have the range of the captured isotopic values or ratios. Okay, so they are non-zero. So what we see is, or what happened is, we had now the same UV. We had the same UV. We had the same UV. This UV, associated the sulfur compound. All right, and then we had that, and then we had that. But now, because we did not have the presence of oxygen, because remember before the great oxidation event, it means we were in the reducing environment or in an oxic environment, the oxygen deficient environment. All right, now because we did not have oxygen, it means after the dissociation happened, all right, the products, they do not undergo what we call the reaction or recombination. So these things were like that. Now, making sure now that the MIF are now preserved in the rock records. It means now the rocks that are older than great oxidation event, they are supposed to show non-zero isotopic ratios, or they are supposed to show the MIF mass-independent fractionation. All right, because after the photochemical took place, these rocks they did not, all right, undergo what the reaction, all right, because one thing that you must understand is in the Archean times, that is to say before 2.45 billion years ago, or before the Great Oxidation Event. So basically what happened is, like I mentioned, that we had this sulfur compound or sulfur dioxide in the atmosphere. Okay, then that was disassociated by what you call the UV radiation. All right, and then this UV radiation did not discriminate between isotopes, and so it fractionated it independent of the mass of those isotopes. And then these fractionated products, they did not recombine. They did not recombine or undergo any reaction, because we did not have any oxygen, because we were in the oxygen deficient environment. Okay, now these isotopic signatures, they got to be preserved in the surface or within the sediments. Okay, because there was no oxygen to react with them, which is why the MIF, all right, the MIF isotopic signatures got preserved in the rock record before the Great Oxidation Event. We are looking at the Transvaal supergroup rocks, for example, in South Africa. We are looking also in the Archean rocks. Okay, because these are the rocks, Archean granites, for example, yes, or Archean basement rocks. So these rocks would have the sulfur isotopes that are showing the MIF. That is to say, they are not following the predictable rules. Okay, and so basically that's what happened. All right, basically that's what happened. So which is why we say MIF signatures such as non-zero are typically found in the rocks formed before the Great Oxidation Event, when Earth's atmosphere was anoxic. So this makes MIF a powerful tool for identifying ancient atmospheric conditions, or determining if sulfur is in younger rocks originated from older Archean sources with MIF signatures. This is to say, for example, if we're looking at the case of the Bushveld Complex, these would be younger than Transvaal and Archean basements. All right. So because now the Bushveld would, for example, would come after the Great Oxidation Event. All right. We don't expect the Bushveld Complex to have, the magma to have the MIF signatures. Because now, after dissociation, we're going to have the reaction because of the presence of oxygen. And then now that when that is happening, it makes the MIF not to be preserved in the rock records. So it means if we were to find the MIF in the Bushveld rocks, the idea would be that the contamination, it happened it means when the magma was rising, it passed through the Archean basement or the Transvaal supergroup rocks. And then it got assimilation happened, and then it got these MIF signatures, and then which is why we'd also see the MIF in the Bushveld magma. That is what would be happening. All right. So, but we are not saying that the what do you call it? The photochemical separation is not happening today. It is still happening today, but the problem is after this association, there's going to be a recombination. There's going to be reaction. Now, making things now MIF signatures not to be preserved. All right. I hope you understand. If you get confused, you are more than welcome to comment in the comment section, and I will be happy to assist. All right. So these are very powerful tools in geology. Okay, these MIF signatures. So tracing contamination using MIF and MDF. So the geologists use the presence or the absence of MIF signals or the non-zero signatures in sulfur isotope to what? To track the ancient atmospheric conditions and the timing of oxygenation event. Because we know, how can you determine this timing? Because we know that the rocks before the Great Oxidation Event, like the Archean rocks, they're not supposed to be showing this MIF. Okay, they're not supposed to be showing this MIF. So, but now, if we see now the rocks showing MIF, it tells us now that we had a shift in the Earth environment. All right. Now, in rocks that formed before the Great Oxidation Event, the MIF signatures provide the evidence of the reducing conditions, wherein the UV photo dissociation, this association of sulfur compound occurred. All right. And then when that disassociation was happening, the reaction did not happen because we did not have any oxygen to combine with with the products. All right. So, but on the other hand, rocks formed after the Great Oxidation Event, they show only mass dependent. They are showing what you call the zero signatures. Okay, so these zero signatures, they indicate the atmosphere had become oxygenated, which is why the products after this association of sulfur oxide or sulfur compound, they reacted and recombined, making sure now that the MIF isotopic signatures are not to be preserved in the rock records. Okay. So I hope this makes sense. I hope this makes sense. Now, so by analyzing the isotope ratios in rock samples, geologists can, track the timing of oxygenation events, trace geological contamination, understand sulfur cycling, identify crustal contamination in magmatic systems. Okay, so let me give you an example. I mean, if you are looking at the tracking of the timing of the oxygenation event, I mean, you'd agree with me that the transition from, the MIF-dominated sulfur isotopes to, mass-dependent dominated isotopes, that transition, all right, that is separated by the Great Oxidation Event. You've seen that a Great Oxidation Event line. All right. This would mark the Great Oxidation Event. All right. If any transition from mass-independent fractionation, dominated sulfur isotopes, and the MDF dominated isotope, it will mark the Great Oxidation Event. And thus, it marks the important shift in Earth atmospheric oxygen levels. Okay, so it means now that if we have the disappearance of the MIF signals in rocks after approximately 2.4 billion years or 2.45 billion years, okay, it will confirm that the oxygen began to accumulate in the atmosphere. Because now, if we did not have oxygen, now we expect to see the mass-independent fractionation signals or signatures. But because now, after 2.45, after great oxidation event, we don't see these MIF signals. It shows now that we are in the oxygenated environment or in an oxic environment, which is why we're saying it tracks the timing of oxygenation event. It shows us that now if we've got this separation, because we expect now the Archean, that is our expectation. The Archean and the, let's just say the modern Earth, let's just say modern Earth. Okay, this shift, the Great Oxidation Event, we expect the MIF this side, but now if we also expect MIF this side, but if we don't see any MIF, but we see MDF, we see what you call the disappearance of MIF signals, then that will tell us that after this great oxidation event, we did not have the oxygen, which is why it helps us to track the timing of oxygenation events. All right, but also it helps us to trace the geological contamination. Okay, so when geologists find the MIF signatures in younger rocks, like the rocks after the Great Oxidation Event, if we see the MIF signatures in these younger rocks, what does it tell us? To us, it suggests. Remember, we are scientists. We are always suggesting. We are always suggesting because we are not 100% correct. We are suggesting. All right. So these MIF signatures in younger rocks after Great Oxidation Event would suggest that the contamination from older Archean sources carried sulfur with what you call Great Oxidation Event MIF signals. So because we know the Archean sources, they carry the MIF signals. So if we see this MIF inside the younger rocks after the Great Oxidation Event, it means the younger rocks were contaminated by the older Archean rocks, which they are known to be carrying the MIF signals, which is why they're also good for tracing the geological contamination. And also by understanding what you call the sulfur cycling. All right. How can I explain? I mean, for example, we know the combination of the MIF and MDF. If you combine MDF and MIF data, that will help the geologist to reconstruct the ancient sulfur cycling processes. All right. That is to say, this would include, the role of microbial activity and atmospheric chemistry in shaping the Earth's surface environment over geological time. All right, over geological time. So it means now the MIF signals in early rocks would reflect sulfur cycling in a low oxygen atmosphere, while the MDF signals in post Great Oxidation Event or the MDF after the Great Oxidation Event, would reflect sulfur cycling in oxygen-rich environment. I hope you understand what we mean when we say to understand the sulfur cycling. But also, they will be good to identify the crustal contamination in magmatic system. Now, because in certain circumstances, magmatic rocks that interact with sulfur-bearing sediments or rocks from the Archean, can what they can incorporate sulfur with MIF signals, like I've explained. All right. Now, geologists, studying this system use sulfur isotopes to detect such crustal contamination. Okay, which would now provide insight into magma evolution and the role of sediment assimilation, usually, let's say, for the mineralization. Okay, so I hope it makes sense. Okay, so let's look at the case of the Bushveld. Okay, let's look at the case of the Bushveld. We know that the nickel, copper, PGE deposits, for example, okay, in these deposits, in nickel, copper, PGE deposit, if isotopes like sulfur, oxygen, and radiogenic isotopes, they play a critical role in revealing the processes of magma county rock interaction and assimilation. All right. So these isotopes, specifically, sulfur, oxygen, and radiogenic isotopes. But in this case, today we are looking at sulfur isotopes. So they will tell us much about the magma county rock interaction. All right. So now the MIF signatures, or the yes, MIF signatures, they would stand out. Okay, they would stand out as highly definitive, and not only definitive but sensitive indicator of sensitive, as a definitive and sensitive indicator for detecting crustal sulfur contributions. Okay, so these CAP33, these MIF values, all right, they can be employed even in the complex multi-stage geological environments. For example, if that kind of environment, we can be looking at the Platte Reef in the Bushveld Complex, in the northern limb of the Bushveld Complex. All right. So geologists studying the Bushveld Complex have employed this MIF of sulfur isotopes to understand the extent of the crustal contamination in the Bushveld Complex, particularly from sulfur-bearing sediments in the Transvaal supergroup or older Archean rocks. Okay, so these MIFs, they will tell us much about magma county rock interaction. So the Bushveld Complex is one of the largest layered mafic intrusions in the world, and is known for its vast reserves of the PGEs, the chromium, and the vanadium. Okay, vanadium in the upper zone, the chromium, and the critical zones, and also the PGEs in the Berensky Reef, for example, when we're looking at the rest of the Bushveld Complex, like the eastern and the western Bushveld Complex, for example. So the intrusion of this magma, into the crust, it involves the magma county rock interaction. All right, because now the Bushveld magma, it intruded the Transvaal supergroup. So we expect that the interaction. All right. So this would always mean that the non-zero MIF signatures, okay, because of being a product of these atmospheric processes. All right, we know that the MIF signatures, it's because of the product of the atmospheric processes, and because of that, it cannot be generated by high temperature events such as metamorphism or hydrothermal alteration. Okay, so these processes, it can only dilute or alter the original CAP33 ratio signals, but you can't create or amplify them. All right, you can't create or amplify them. So it means these high temperature processes, they can only dilute, but they cannot create or alter these things. All right. So because of that, the values, these MIF values, they would serve as a unique fingerprint of the original sulfur source. They are like human fingerprint. All right. I hope you understand what we are talking about. So okay, so let's go to this one. Like we already mentioned that the Transvaal supergroup, if you can check here, this is the time during which the Transvaal supergroup rocks were deposited. This is from Penniston Dolan, 2006. She did a lot of work on the MIF, okay, on CAP33. Now, if you can check now, early atmosphere, the modern atmosphere, it's showing this mass-dependent fractionation. All right. Now the Cat 33 is right on the zero. All right, on the zero line. But now, immediately, when the Bushveld complex intrudes the Transvaal supergroup, the Bushveld complex also start to show these signatures, these MIF signatures. But now we ask ourselves, why the because we know that the pristine Bushveld magmas are not supposed to show the MIF values. But now we see these MIF signatures. Then one of the suggestions would be that because the Transvaal supergroup would be having the MIF signatures. It means when the Bushveld complex was passing through the Transvaal supergroup, it incorporated or assimilated these MIF signatures, which is why the Bushveld complex, even if it's after the Great Oxidation Event, it still preserves the MIF isotope signatures. All right? So I hope you understand what we are trying to say. Because even here, the mass-dependent fractionation, these are the zero lines. But now, if you get to deviate away from the zero line, you show the MIF signatures. So the MIF signatures, they tell us much about the crustal contamination. But now, if we were to yes, the implications of the magma, implications for magma evolution, okay? And then MIF as a tool for mineral exploration. We want to tell you how now they're using this MIF to understand much about the magma evolution, to also, help, during mineral exploration, and also during the to determine the multiple contamination sources. Now, basically what's happening is, if you identify the crustal contamination through MIF signatures, this would help geologists to, understand the evolution of the Bushveld magma, for example. All right. Because now if they see the MIF signatures inside, then it tells that there could have been contamination. It means during the magma ascent, it incorporated the crustal material, which is why it's still showing the MIF signatures. So now, meaning that now contamination get to influence the sulfur content and oxidation state of the magma, which would in turn affect the mineralization processes that would now concentrate economically available metals like what PG is, for example. Okay, because we know that assimilation of sulfur-bearing sediments, can increase the sulfur content in the magma. So if now we've got sulfur content in that particular magma, what will happen? This would lead to the formation of the sulfide minerals. Okay, now the sulfide minerals, we know they host the PGEs. Now, as the exploration tool, we know that geologists can use the MIF signals, not only to trace contamination, okay, but also to predict the presence of sulfide minerals in certain layers of the Bushveld complex. Okay, so once they have, they've predicted the presence of the sulfide minerals in Bushveld layers, what will happen? But we know that sulfides, they play a crucial role in concentrating the PGEs. Once we have got the sulfide, then we know these things, they play a very important role in concentrating the PGEs. So it means as geologists, by understanding where contamination occurred, would guide the exploration efforts for platinum group elements. It means now MIF signals or MIF isotopic signatures would serve as a geochemical fingerprint that would reveal much about the interaction between between magma and the country rock. Okay. Now that would help geologists to pinpoint areas of enhanced mineralization because of these MIF signatures. Okay. I hope you understand what we're trying to say. And also, in the case of the multiple contamination sources, like the Bushveld complex, may have been, contaminated by multiple sulfur sources at different stage of its evolution. Like, the case of Magahais et al. 2018 and 2019, the study showed contamination by multiple sources. All right, this is the case. So it means now, how can you tell much about the multiple sources? Okay, so when you're using the sulfur isotope analysis, combining the mass-dependent fractionation and mass-independent fractionation signatures, the geologists would be able to differentiate between the different contamination events, because now they're using the combination of the two. They'll be able to know the different contamination events. For example, I can give you an example of the early contamination. We can have early contamination from Archean rocks that may leave a distinct MIF signatures. Then later on, we can have the contamination from the Transvaal supergroup rocks, okay, which results in different sulfur isotopic or isotope patterns. So you can tell that we've got different signatures. Okay. Now, the most important part also is we've got different school of thoughts for the formation of the Bushveld complex. All right. So one of the models for the formation of the Bushveld complex is what you call the offstage. All right. That's what you call the offstage, which has been recently found, I think 10 years ago, maybe. Yeah. Okay. Yeah. So the recent studies are doing that. So basically, they want to understand if the contamination happened in the in the deep staging chamber. All right. The contamination happened in the deep staging chamber. All right, in the lower crust, or the contamination happened in the upper crust during the emplacement. They want to understand that difference. All right, because now let me give you an example. All right, so if let's say this is the emplacement, this is where the Bushveld magma was in place. I'm just giving you an example. And then let's say this is the deep staging chamber. Okay, so contamination can happen here. Okay, contamination can happen here, and then a recording, let's say, a MIF signatures here in the deep staging chamber. Now, contamination happened here in the lower or in the lithospheric mantle, okay, in the lower crust. Okay, it can happen here. Now, this magma, it goes up and get to this Bushveld magma. It gets to be emplaced. So when it's emplaced, let's say we've got stratigraphic sequences of the Bushveld complex. Let's say A, B, C, D, for example. All right. So all these stratigraphic sequences, if they get to show the MIF signatures, let's say we see MIF, we see MIF, we see MIF, we see MIF, then what will be the assumption? The assumption would be that, oh, why all these stratigraphic sequences show the MIF isotopic signatures? So it means now the contamination happened in the deep staging chamber. All right, the contamination happened in the deep staging chamber, and remember the contamination from either the Transvaal, for example, in the Bushveld complex, even if it's not the Bushveld complex, for example, like we can use other magmatic systems. All right, if it happens in the deep staging chamber, the rocks before the Great Oxidation Event, they would now come up with their MIF signatures, now making the magma to have MIF signatures. Now, if the magma get to be in place like that, A, B, C, D, all these stratigraphic sequences showing the MIF signatures. What does it tell? It tells us that the contamination happened in the deep staging chamber. Okay? Because now we are looking at the stratigraphic patterns. Because when we're looking specifically at these stratigraphic patterns, if the assumption would be that if the signals are found throughout all the stratigraphic sequence A, B, and C, okay, of the Bushveld complex, it would mean, especially even here, even the lower units, because usually we expect this, let's say A, to be in contact with the footwall rocks, to be in contact with the footwall rocks. It can be Archean basement granite, or it can be Transvaal supergroup, for example. So these are the footwalls. So even if we see this MIF from the lower units, which are in contact with the footwall rocks, which we know they are also containing MIF, and also the upper sequence, they're also containing MIF, then we understand that no, this is not contamination by these footwall rocks here during the emplacement. The contamination did not happen during emplacement, but the contamination happened when the magma was still in the deep in the magma chamber, what you call the deep staging magma. Because if the signals are these signals, because these signals are not restricted to, or are not localized, are not restricted to, a specific stratigraphic levels, they are seen everywhere. Now would say we had what you call the deep staging magma. I hope you understand. But now, if we have got because of, for example, we know the proximity of for example, some of the sequences to, the country rocks, okay, or crustal rocks. So if signals are stronger in regions where the Bushveld complex interacted with sulfur-rich rocks, for example, from the Transvaal supergroup or from the Archean basement, okay, it will suggest the emplacement-related contamination, because we only see the MIF signals only here. The MIF signatures are localized. So if they're localized, they're only seen in a particular stratigraphic sequence, especially in sequences that are close to the footwall rocks. Then this would suggest that now the contamination happened during the emplacement, because all these signatures, they are only, localized. They are only seen in specific areas, in the specific stratigraphic levels of the Bushveld complex. Then now that will suggest that the contamination happened during the emplacement. But if we say that these MIF signatures, they are seen in all, they are not localized, they are seen in all stratigraphic sequences, then it means now that the MIF signatures, or the contamination, it happens in the deep staging chamber. This is exactly what the recent study they are trying to, to check what you call the evolution of the magma, and to understand the formation of, for example, of the Platte Reef, of the Flat Reef, and the Merensky Reef. All right, yeah. So I hope this makes sense. I hope this makes sense. This brings us to the end of our session. For references, you can look at the study of Pennington Doland, not only 2006, Pennington Doland 2006, 2008, 2012. He did extensive work on the multiple sulfur isotopes. And if you want to understand this mass difference, mass-dependent and mass-independent, of course, see other, these authors here. And yes, also Shaman with Pennington and Kinnett and next, you can name them. They did these MIF signatures. So you are more than welcome to visit the references and um, try to enhance your understanding. So without any further waste of time, let me thank you guys for joining us today, for tuning in. Don't forget to like, share, comment, and subscribe to our content so that we keep producing this kind of our content. And please don't forget to share. All right. So this brings us to the end of our lessons. And I will always like to say, until next time, cheers.